Most of the time, the universe feels like a grand, balanced machine. Stars burn steadily, galaxies spin in elegant spirals, and on the largest scales, everything seems to follow a predictable rhythm. Gravity pulls things together, forming the structures we see: planets, stars, black holes. But zoom out far enough, and the picture flips. The universe isn't just expanding, it's accelerating, as if some invisible force is shoving everything apart faster and faster. We call that force dark energy, the mysterious 70% of the cosmos that we can't see, touch, or explain. At the other extreme, black holes lurk as cosmic vacuums, swallowing light and matter, compressing infinity into points of no return. One tears things in, the other pushes them out. Opposites, right? Except, what if they're not? What if black holes and dark energy aren't enemies, but siblings born from the same quantum cradle, woven from the same threads of reality? That's the question at the heart of this video. Not some wild speculation, but a growing body of research suggesting that the quantum weirdness inside black holes could be fueling the universe's runaway growth. It's an idea that bridges two pillars of physics, Einstein's gravity and quantum mechanics, in ways that could rewrite our story of the cosmos. Because if black holes are secretly pumping out dark energy, then the universe isn't just expanding. It's evolving in ways we never imagined. When we talk about black holes, we usually picture the monsters from general relativity, regions where gravity wins so completely that space-time curves into a trap. Anything crossing the event horizon, that invisible boundary, gets spaghettified, stretched and crushed toward a singularity, a point of infinite density where the laws of physics as we know them break down. These beasts form from dying stars or mergers, and we've spotted thousands, from stellar remnants a few times our sun's mass to supermassive behemoths billions of times heavier, lurking at galaxy centers. Black holes are endings, devourers of information and light. But quantum mechanics whispers a different tale. Enter Stephen Hawking in the 1970s. He showed that black holes aren't eternal prisons. Near the event horizon, quantum fluctuations, those fleeting pops of virtual particles in the vacuum, create a glow of radiation that slowly evaporates the black hole over eons. Hawking radiation isn't just a leak. It's a crack in the door, hinting that quantum effects can pierce the veil of classical gravity. Yet this leads straight to the black hole information paradox. Quantum rules say information can't be destroyed, but if a black hole evaporates completely, where does all that swallowed stuff go? It's like burning a book and expecting the words to reappear unscathed. This paradox has haunted physicists for decades, forcing us to confront that general relativity and quantum mechanics don't play nice together. We need quantum gravity, a theory of everything for the extremes. And here's where dark energy enters the stage, uninvited but insistent. Dark energy burst onto the scene in the late 1990s, when astronomers measuring distant supernovae realized the universe's expansion isn't slowing under gravity's tug, it's speeding up. Something's counteracting the pull of all that matter, diluting the cosmos like yeast in rising dough. We don't know what it is, but it behaves like a constant energy density baked into empty space itself, pushing outward with negative pressure. In the Standard Model, it's the cosmological constant, a tweak Einstein added and regretted to his equations. But quantum field theory predicts a vacuum energy 120 orders of magnitude too huge, the infamous cosmological constant problem. It's like calculating the height of a building and getting a number bigger than the observable universe. Dark energy makes up 68% of everything, yet it's a ghost. Uniform, invisible, unchanging. Or is it? Recent hints from surveys like the Dark Energy Spectroscopic Instrument, DESI, suggest it might evolve over time, varying slightly as the universe ages. This wobble challenges the constant idea and screams for a new explanation. Enter the radical proposal. What if dark energy isn't a separate ingredient, but a byproduct of black holes themselves. Not the classical traps of Einstein, but quantum-tinged ones, where the vacuum's fizzles and the horizon's quantum dance generate the push we need. To understand this connection, we have to dive into cosmological coupling, a theory gaining traction since 2023, born from the unlikely marriage of black hole growth and cosmic expansion. Picture a supermassive black hole at a galaxy's heart. In classical terms, its mass is fixed. It gobbles stars and gas, but doesn't spontaneously bulk up. But tweak the math with quantum gravity in mind, and something wild happens. As the universe expands, the black hole's event horizon stretches, not because it's eating more, but because space-time itself is dilating. To keep the horizon structure intact, the black hole must gain mass proportionally, drawing energy from the vacuum. This isn't free lunch. It's a quantum handshake. The added mass manifests as vacuum energy, a repulsive force that accelerates expansion. In essence, every black hole becomes a tiny dark energy factory, its growth tied directly to the cosmos's scale factor. It's like the black hole is breathing with the universe. As space swells, the hole inhales quantum vacuum energy, exhaling it as the push that drives us apart. This idea, fleshed out by physicists like Duncan Farah and colleagues, resolves a puzzle. Why do red and dead elliptical galaxies, dormant ones with no fresh fuel, have black holes that seem to grow faster than expected? Observations of 341 such galaxies show their central black holes ballooning by up to 7% over the universe's age, perfectly matching the dark energy density we measure today. No new particles, no exotic fields, just black holes doing what gravity demands in an expanding universe. But is this quantum at its core? Absolutely. Cosmological coupling leans on the holographic principle, that mind-bending idea from string theory and black hole thermodynamics. All the information inside a black hole is encoded on its two-dimensional horizon, like a hologram projecting 3D reality. Quantum fluctuations near the horizon, those same ones birthing. Hawking radiation could encode the vacuum energy that couples the hole to cosmic growth. Recent models, including 2024 simulations, show how primordial black holes from the early universe formed in the quark-gluon plasma right after the Big Bang might seed this process, their evaporation and growth, injecting just the right amount of energy to kickstart acceleration around 6 billion years ago. And it's not just theory. DESI's first-year data from 2024 hints at evolving dark energy that aligns with black hole formation peaks during the star-forming heyday 10 billion years back. Coincidence? Maybe not. As Duncan Farah, astronomer and theoretical physicist, put it, this is the holy grail of theoretical physics, a way to tie quantum information preservation to the universe's fate. Of course, not everyone's convinced. Critics point to timeline hiccups. Black hole quasars peaked 10 to 12 billion years ago, while dark energy's dominance ramped up around 8 billion, a 2 billion year gap that's hard to bridge without fine-tuning. Others worry it double counts energy. Black holes are already tallied in the 5% ordinary matter budget, so how can they also be 70% dark energy? Proponents counter that the coupling extracts vacuum energy without violating conservation laws. It's a redistribution, not creation. And quantum gravity theories like loop quantum gravity or emergent gravity from Eric Verlinde bolster this, suggesting gravity itself emerges from quantum entanglement, making black holes natural hubs for dark energy production. Imagine virtual black holes fleeting quantum echoes in the vacuum, popping in and out, their collective tidal forces subtly warping space-time to mimic repulsion. A 2025 paper even proposes non-singular black holes, free of singularities via quantum bounces, radiating in ways that could seed dark energy across the cosmos. This isn't just about plugging holes in our models. It's a portal to deeper truths. If black holes birth dark energy, then the universe's acceleration isn't a bug, It's a feature of quantum gravity at work. Galaxies aren't isolated. Their hearts pulse with the cosmos's rhythm. Entanglement, linking the smallest fluctuations to the largest scales. Einstein, who wrestled with his cosmological constant as the biggest blunder, might have smiled. His static universe dream twisted into a dynamic one, where black holes, those ultimate curveballs, hold the key. Hawking, too, would have loved it, his radiation now the spark for cosmic pushback. As physicist Nyash Afshorty notes, at first blush, black holes and dark energy seem to have nothing to do with each other, but I'm personally excited about it. It challenges our view of endings. Black holes aren't tombs. They're engines, recycling quantum whispers into the force tearing reality apart. Zooming back, this black hole dark energy link isn't settled science. It's a frontier skirmish. Upcoming gravitational wave detectors like LISA could spot horizon ripples from coupled growth, while Euclid's dark energy maps might confirm the evolution. Quantum simulators mimicking horizons using Bose-Einstein condensates are already testing vacuum energy flows. But if it holds, it flips the script. Dark energy isn't dark because it's hidden, it's emergent. A quantum echo of black holes echoing the Big Bang's quantum fire. The universe isn't a clock winding down. It's a hologram breathing, where collapse and expansion dance in quantum harmony. We're not just observers. We're threads in the weave, pulled by forces born from the void. So next time you gaze at the night sky, remember, those pinpricks of light hide monsters that might be saving the show, pushing us toward infinity, one quantum heartbeat at a time. What if the end of one story is the beginning of the whole damn thing? That's the universe for you. Solid until you look closer, then everything connects.